in order to fill out all the key features of the given function here, we will also refer to the graph to understand and explain the numbers that are responsible for certain shifts, okay, and horizontal stretches and vertical stretches and things like that, the frequencies, the period, etc. Notice this graph right away is not going to be exactly representative of this function. Some parts of this function, like numbers, certain coefficients that we're going to take a look at that are responsible for amplitude, stretches, etc., will be explained by the graph. Okay, so we're going to start with the amplitude. As you can see, I've written the formula for this kind of function with the basic constants and coefficients that we will explore, the A, B, and C, and D. So as you can see, the amplitude is going to be responsible. To find the amplitude, you will just need to take the absolute value of the A coefficient. In this case, A is -2. So absolute value of -2 is 2. Okay, so now I'm going to explain to you what an amplitude is. You can see the parent function sine x. As you can see, this is the simplest function for the sine you can have. Way simpler than this. So when it comes to the sine x, the amplitude, as you can see here, is 1, right? Because the A value is in front of the sine. That's the coefficient of the sine here. And as you can see, there's a 1 multiplying the sine, right? So there's a 1. What this means is that the distance between the midline and the highest point is 1. And the absolute distance between this midline and the lowest point is also going to be 1. Even though it goes down, the absolute value of that, the absolute distance, is also 1. So this is what the amplitude does. As you can see in the revised sine function, we have an amplitude value of 2, right? Because the absolute value of 2 is 2. Okay, so what that does, that basically makes the highest and lowest points higher now by a factor of 2 than it was before, right? Before it was 1, now it's 2. And the same thing for the bottommost point. The bottommost point will be -2, right? If midline is at the x-axis. Now midline is always the middle line about which the sine function or cosine function will oscillate. Right? So it goes up, down, up, down. So the midline is right between the highest and the lowest point. Okay? So the amplitude just serves to tell you how far up or how far down it will go. And the absolute distance between the midline and the highest and the midline and the lowest points will be the same. Okay? So that's what the amplitude simply does. Now the next part is the frequency. To find the period. To find the period, we will need to take 2 pi and divide it by the b value. In this case, the b value is 3. So now I'm going to explain to you what a period is. So the period basically tells you the distance in the x value from the starting point here to where the sine function will start to repeat itself, at which it will start to make another copy of it. So as you can see, the full sine wave travels once, it ends there, and then it goes another, right? So that's a full period right there. So one complete cycle is one full period. So in this case, the period is going to be 2 pi over 3. Now, why 2 pi, you might ask? You understand why divided by 3, that's the formula, but why 2 pi? Because the standard period for a sine function, for parent function sine x, is going to be 2 pi. And as you can see, it makes sense with the formula as well, right? Because you take 2 pi, you divide it by the coefficient of x in the angle, like it was here, but it was 3, but this time it's 1. 2 pi divided by 1 is 2 pi. So as you can see, this makes the period way longer in the parent function than in the shorter function. You see, this is sine 3x. As an example, what the 3 does to the period. It makes the period 3 times smaller than it was before for the parent function. Right? So 2 pi over 3 is the period this time. So 2 pi will always be on the top because the standard period for a sine function, parent function, is 2 pi. That's why you take that reference 2 pi and divide it by the coefficient of the x in the angle. Okay? Now the next part is the frequency. How do you explain the frequency? Frequency tells you how many copies or how many full cycles of the sine function in this example are going to be per each unit 1. right? Per each unit. So basically per the x distance of 1, how many copies of sine x will you have? How many full cycles, right? So as you can see, the easiest way to calculate this frequency is to use the period. The period just needs to be flipped, right? You flip this fraction or divide 1 over this, that will be the same thing, right? So in this case, it's going to be 1 over 2 pi over 3, which is the same as flipping it. 3 divided by 2 pi. Now let's verify that. Let's verify that the frequency is really 3 over 2 pi. Notice that I said that the period, the frequency is the number of copies per unit 1. Notice that 2 pi divided by 3 is 6.28 about divided by 3, so that's about nearly 2 units, right? That's the full period, okay? That's the full period. So that means it's talking about 2 units, right? Because per unit is the frequency, but the full period is 2 units. So that means per each unit, we will only have a frequency of about a half. And as you can see, this confirms this result, right? Because 3 divided by 2 pi is about 0.47, right? So 0.48, I should say, right? It's rounded to the nearest hundredth, right? 0.48. As you can see, it's about a half, which it should be. Now, the next part is the midline. The midline, as you can tell, like I explained before, midline is going to be in the middle between the highest point and the lowest point, right? It will always oscillate, the sine or cosine functions will oscillate about the midline point, always, right? So now the midline, as you might have guessed, is the equation of a horizontal line. In this case, the midline is going to be this shift here, right? The midline is always the value of d. In this case, plus d is equal to -5, so that's the same thing as saying d is equal to -5. So you're going to say y is equal to -5, okay? So the midline is going to be at the horizontal line -5 for the y value, right? So it's going to be 5 units, the midline for this example is going to be 5 units below the x-axis, and it will be parallel to the x-axis, right? Because it's horizontal, y is equal to -5. Now, the next thing is the phase shift. Phase shift is responsible for left or right shifts, right? Positive or negative shifts from the standard position. In this case, the shift is going to be calculated by taking the c value and dividing it by the b value. The c value here is not 4, be very careful, because negative c is equal to positive 4. So that means positive c is equal to -4, right? If you solve for c. So that means -4 divided by 3 is going to be the phase shift. -4 over 3. You might say, but I actually saw, some students tell me, I actually saw the 3 outside the parentheses, right? That's fine. We can write -2 sine 3, right? We can write 3 outside, that doesn't matter. But then making sure that since we took 3 outside, it will no longer be a 4, because 4 times 1 outside is 4, but we need to keep it to be a 4, so we have to divide 4 by 3, right? So that the 3's would cancel out, and it would be a 4 like it was before, right? That's fine. And then -5. In this case, notice the result will still not change because the phase shift will still be -4 divided by 3. Right? Because if you divide -4 over 3 by 1 here, it will still be the same, right? And the negative doesn't change, right? Because the c value in this case is going to be -4 over 3 because there's a -c, right? So it doesn't matter if you take the 3 out, right? You just have to be careful to write this fraction 4 over 3 because it would cancel out with the 3's and give you a 4. Because before it was just a 4. If you fail to divide it by 3, you will get a 12, and that's not right. 4 times 3 is 12, but there was no 12 there, right? There was a 4 there. So that's why you got to be careful. But still, the concept is the same. You still will divide 4 over 3 divided by 1 here, and you will get -4 over 3, right? Negative. So that's the phase shift. It tells you that there will be a phase shift to the left, right, of the parent function sine x. It will be shifted to the left by 4/3 units, 4/3, right, to the left. That's why there's a negative. Okay, Now, the vertical shift, as you might have guessed, it has a lot to do with the midline, actually direct relationship with the midline, because we already talked about the fact that the midline is the equation y is equal to -5. So that means you're taking the standard position sine x and you're moving it 5 units down, right? So the vertical shift is precisely the d value, -5. So the only difference with the vertical shift and the midline is that you set y is equal to d. But here you just take the d value and you write it, right? So the vertical shift means we shifted 5 units down. We take the parent function sine x and just shift it without changing the way it looks, just shift it down 5 units. Now here comes an interesting part. So horizontal stretch shrink and also the vertical stretch shrink or none. So in this case, there will be no none. So we're going to cross that out. That's not going to be applicable. In this case, we definitely will have stretches. So how does this work? So the horizontal stretch, let's start with the vertical stretch actually. The vertical stretch is going to be affected by the amplitude. So in this case, the amplitude is 2. Okay? So whenever taking a look at the parent function sine x, the amplitude was 1, right? So that's the parent standard function that you know. But whenever the amplitude is greater than 1, in this case, right, 2, it means that you're making it larger, right? The highest and lowest points are further away from the midline. So you're kind of stretching it, right? You're vertically stretching. Imagine that you're pulling it from this upside here and from the downside. You're pulling it in both opposite directions, up and down, right? You're stretching, right? You stretched it so it became like a brown one, and notice that the coefficient here is 2. The amplitude is 2 and not 1 like it was before, right? So there is a vertical stretch. Okay, so we must, vertical stretch, right? So we must circle that. Now, horizontal stretch is going to be determined by the coefficient of this x, by the b value. Now take a look here. Notice that originally the period, notice that it also has to do with the period. The period was 2 pi divided by 3. The normal period was 2 pi in the standard sine x. Now it's 2 pi divided by 3. So basically what you made a period 3 times smaller than it was before. So you kind of squashed it. You squashed it horizontally on both sides. Imagine that you're squashing it with your hands horizontally, this parent function. You're squeezing it on both sides to such an extent that it became so small, right? Speaking horizontally, it's squashed, right? So that means whenever the b value is greater than 1, right? 1 is the standard function. Whenever the b is greater than 1, you squashed it from the sides, right? So you made a horizontal shrink, right? You shrinked the function. So there's a horizontal shrink in this case. Okay? So, and once again, the horizontal stretch or shrink depends on the value of the b. When the b is less than 1, you might ask, what happens when the b is less than 1? Well, when the b is less than 1, guess what happens? The period would have been even longer than it was. If the period is longer, you're stretching horizontally. Imagine that you're pulling this end and that end of the sine function. You're pulling it in opposite direction. You will actually stretch it, right? Even though the amplitude will still stay the same, if you will keep it to be 2, you will stretch it to such an extent that it will be a horizontal stretch. Now, when it comes to the vertical stretch, you might ask, when does it shrink instead, the vertical shrink? Well, whenever the amplitude is less than 1. Right? Whenever the amplitude is less than 1. If it's less than 1, the absolute value is less than 1, you will make the spikes smaller than they were, right? So the spike will not be up to here, it will be lower, right? It will be, the spikes on both sides of the midline will be closer to the midline. So basically what that means is that you're vertically pressing the sine function, the parent sine function, to make it closer to the midline, right? To squeeze it from the upside and from the downside. Instead of stretching it like we talked about before, vertically, you're going to be pressing it vertically on both sides, right? So you're basically going to be shrinking vertically in that case, whenever the amplitude is less than 1, all right? So in this case, the amplitude, the absolute value was greater than 1, it was 2. That's why there was a vertical stretch. The b value was greater than 1, and when it's greater than 1, you're talking about shrinking horizontally, right, to make it really small here. As you can see, horizontally, the period is 3 times smaller than it was, right? So that is a horizontal shrink. Now, here comes the domain. What about the domain? The domain is going to be the list of x values for which the function is defined. As you can see, there's no x value that will ever keep the function from being continuous, right? You will just endlessly keep repeating itself forever and ever and ever, right? So there's no way that there's an x value that does not work, right? There's no x value like that. All the x values work. So we're going to say all real numbers. Now, to find the range, you just need to find the lowest point and the highest point, right? Because the range is the list of y values, right? The vertical values for which the function is defined. So how do you find the range algebraically? The range algebraically will be what? So let's see. The lowest point is going to be the midline. Or maybe I should not say midline, I should say instead the d value, right? So the d, so I'm going to say the coordinates, right? And keep in mind that we're including the bottommost point because the function is defined, the sine function is defined at the bottommost point, right? So we include it with a bracket. So the formula is going to be d minus the amplitude. The absolute value of the amplitude, right? The absolute value of the amplitude, right? So that's going to be this. Okay, and then the comma, and what is going to be the highest point? The highest point is going to be the d value plus, right? Because this makes sense, right? You're subtracting from the midline to get to the lowest point, right? You go further down by subtracting the absolute value of the distance, the amplitude, to go to the bottommost point. And here you're going to add to the midline coordinate to go higher, right? To go as high as possible, right? To the highest point. So you're adding the absolute value of the a here, of the amplitude. So that gives you what? That gives you negative 5 minus 2, right? And then this gives you negative 5 plus 2, right? So that means the range, and I'm going to indicate this with blue because these were the steps we took. The range is minus 7, minus 3, okay? So the lowest point is minus 7 and the highest point is negative 3, okay? Now, we're done with the sine function. Now let's talk about the tangent. The tangent is going to be similar, okay? The amplitude is found by taking the absolute values of 1/3. You get 1/3. The period is going to be interesting now. The period. Now notice that when it came to the sine function, we talked about 2 pi being divided by the b value. Here is going to be the same thing. We're going to divide it by the b value. In this case, b is going to be 2. But you might say, is it going to be 2 pi now? It's not going to be 2 pi. It's going to be pi. Now, why is it pi this time? Why is it pi for the tangent function? Notice in the given graph, the standard tan of x parent function has period from negative pi over 2 to pi over 2, right? That's just one cycle of it, right? And there are asymptotes on both sides because the tangent function is undefined at x is equal to negative pi over 2 and at x is equal to pi over 2. So it never hits the asymptotes. It will go forever down, closer as it goes down here, closer to the negative pi over 2x value, and it will increase forever as it gets closer and closer to the x value of pi over 2. So it never hits it. That's why these are asymptotes. So as you can see, the period from negative pi over 2, the distance, right? The distance from negative pi over 2 to pi over 2 is going to be precisely pi, right? Because negative pi over 2 to 0, right, the meeting point here, is going to be pi over 2, the absolute distance. And the next distance is going to be from 0 to pi over 2. Add those two together, pi over 2 plus pi over 2, bingo, pi, right? So the distance from negative pi over 2 to pi over 2 is pi, and that stands for the period. That's why we're taking pi over 2 and not 2 pi over 2. Because for the standard sign, it was 2 pi that was the full period of the parent function. 2 pi. In this case, pi is the full period, right? And I should say that you start at 0 here. Okay, and I'm going to indicate that just so that you understand the x value. So this starts from 0, and this goes up until 2 pi. Right? That's a complete period for the standard sine function. For the tan functions, from negative pi over 2 to pi over 2 as one cycle. Now this period here, if we understand what it is, it's going to be about 1.57. 1.57. So basically what it tells you is that it takes about 1.57 units for the full cycle of this tangent function to occur. Okay, before the copy is produced on the right side. So now the frequency is taken by flipping this, of course, 2 divided by pi. Let's see what that is. That's about 0.64, so about 2/3. So what that tells you, let's see if this result makes sense. So we know frequency is the number of copies of the tan function we will have per each unit, right? Per each unit. But each period takes more than 1 unit, right? It takes 1.5 units. So 1 out of 1.5 units is about 2/3, right? And that makes sense with the frequency result 0.64. So now the next one is the midline. The midline is going to be similar, right? As you can see, you can treat the point of intersection here as the origin. And this is exactly the origin, right? Between negative pi over 4 and pi over 4 is going to be the origin. And notice also I forgot to mention that the period is pi over 2. You can definitely tell that this will be the tan of 2x is the reference graph for when it comes to having a coefficient of 2 for the b value. It makes it shrinks the graph horizontally, right? So it definitely shrunk compared to the parent tangent function here. So as you can see, what happened was the period is twice as small now, right? So that 2 makes the period smaller because pi divided by 2, not divided by 1 this time. And as you can see, also the asymptotes are also being divided by 2, right? Negative pi over 2 divided by 2 is negative pi over 4. And the same thing for the positive side, positive asymptotes as well. Pi over 2 divided by 2 is pi over 4, right? So also the asymptotes follow the same pattern as well, mathematical pattern. So the midline in this case is going to be the line through which the origin is passing. But that's in the standard position though. What if there is movement, right? If there's vertical shift, we're going to follow the d value. Just like in the sine example, y is going to be set to the d value. The d value in this case is 4, right? So that tells you you're taking this, suppose that this is the x-axis. Well, this is the x-axis, right? And the tangent function is drawn, the standard tangent function. You're moving it 4 units up. That's all you're doing with the midline, right? You're moving 4 units up, and the midline will be the equation y is equal to 4, the line parallel to the x-axis. Now the phase shift, right? This is the horizontal shift, right? So the coordinate responsible for that will be the b, right? So you're taking c and you're dividing it by the b, right? C in this case is 1. And the b value is 2, right? So the phase shift is 1/2. So basically what this tells you is that you're going to move 1/2 units the standard position tangent equation to the right because it's positive. Now the vertical shift will be the d value, right? So that's going to be positive 4. We know that. Now let's see, the horizontal stretch shrink none. So horizontal, definitely this is not going to be none. As you can see, we have b value which is not equal to 1, and a value which is also the absolute value, right? The amplitude is also not equal to 1, right? So definitely none will be out of the question. There will be vertical and horizontal stretches or shrinks, etc. So I already mentioned that horizontally we shrunk the given tangent function. We shrunk it, right? As you can see, you squeezed the parent function from right and left and made the period twice as small as it was before, right? It's not pi, it's pi over 2 now, right? So you're definitely talking about horizontal shrink, right? So let's mark that. This is the right answer. Now in the vertical stretch shrink here, notice that there's a 1/3. The absolute value is 1/3. 1/3 is less than 1. Remember, when it's less than 1, it means that basically the parent tangent function will rise slower, right? It will have the same period, right? This thing does not, a value, the absolute value of the a does not affect the period, right? The period stays the same, as you can see with the green one, 1/3 tan of x, has the same period, but it rises slower and it goes down slower as well. And that's responsible for the 1/3, right? Because 1/3 is smaller than 1. So it makes sense that it should rise slower than when there's a 1 multiplying the tangent of x, right? So what this basically means is that you're squashing vertically from the upside and the downside, you're squashing this tangent function and bringing it closer to the midline. So you're basically shrinking also. You're also shrinking this vertically, right? So in this example, you're shrinking horizontally from the right side and the left side to make it look like the red one, and also you're shrinking it vertically, right, to make it look like the green one instead of the original black one. And as I told you, these are not typical representations of the given graph. They're just telling you independently what would happen when there's an a value that is not 1 and when there's a b value that is not 1, right? It doesn't take into account the shifts, the vertical shifts, etc., etc., etc. And it doesn't give you the horizontal shrink and vertical shrink at the same time, right? These are separate graphs for each type of the horizontal and vertical changes, okay? Now, when it comes to the domain is going to be what? Notice that we were talking about the asymptotes. We were talking about the asymptotes before. Notice that to find the domain, recall that in the tangent function, this is a complete angle representation. 2x minus 1 is a representation of an angle. So what we can do, we can set 2x minus 1 equal to the angle measure that makes the tangent undefined, or the x value that gives us the asymptote. In this case, minus pi over 2. Or let's do it positive pi over 2, just for avoiding the negative sake, right? So we're going to set this to the asymptote x value of pi over 2. Then we can solve for x. So x is basically equal to pi over 2 plus 1 divided by 2, right? So 1/2 plus pi over 4. So now what this tells you, and notice that 1/2 plus pi over 4, also the period was what? The period was pi over 2. So each time there's an added pi over 2 to this x value, or subtracted pi over 2 value from this x value, you will have an asymptote, and you will have x values at which there will be that will not be part of the domain, right? These x values. These asymptotes are not part of the domain, right? So the way to express that is to say that x does not equal to 1/2 plus pi over 4 plus minus, because asymptotes are continuously on the right side forever and on the left side forever, right? They always continue to exist, right? At the increments of the period, right, being subtracted or added to the given x value here, 1/2 plus pi over 4, right? That's why plus minus, right? Plus minus. But how do you account for endless numbers of these asymptotes? Well, you're not going to just plus minus pi over 2. That's not enough, because you need all the possible multiples of pi over 2, right, on both sides, the left and the right. So you're going to do n plus minus n pi over 2, and then indicate in parentheses n any integer, right? That makes sure that you will have an infinite number of asymptotes on the right side of this current x value asymptote, 1/2 plus pi over 4, and also on the left side, right? Because this accounts for the minus, right? Subtracting n pi over 2, n being any integer. Now the range is going to be, again, now here's the thing. The range, as you can see, as I told you before, the tangent falls infinitely, right? As you can see. And it doesn't matter if it's shrinking or not, the behavior is the same. It will fall as gets closer to its respective asymptote, and it will rise forever as it gets to its respective positive asymptote on this side. So basically the range is going to be from negative infinity to positive infinity, right? Because these are the vertical values for which the function is defined. And the vertical values, there's no value that does not define it, basically, right? Infinitely down, negative infinity. And notice I'm not bracketing it because we're not including the infinity. Negative infinity or positive infinity cannot be measured quantitatively, right? It's not a quantity. We cannot measure it. We cannot include it as our closed point. So I hope this was a lot of help. I know this has been a lot of information, but I just wanted you to understand how all the key features work, how to use the graphical representation to understand the stretches, horizontal, vertical, etc., the midline, the phase shifts, etc., frequencies, periods, amplitude. So I hope it was helpful, and thank you so much. See you in the next video.